Well, this is a interesting, maybe a little bit tricky proof. It's theorem 12.5. Tangential and normal components of acceleration. If r of t is a position vector for a smooth curve C that has a unit normal vector n of t, then the tangential and normal components of acceleration can be found by the tangential component is the derivative of the length of the velocity vector that comes from here. And now here's the part that's kind of unique. That's the acceleration vector times the unit tangent vector. And here's the easy way. Vector v, the velocity vector, times the acceleration vector divided by the length of v. And the normal component of acceleration is just what you'd expect. We would start out with maybe this, change it to this, which becomes this, but here we go. Actually becomes this, maybe is another way to do that. But let's see what we can come up with that might be easier than that. Of course, first it's the length of the velocity vector times the length of the derivative of the unit tangent vector. That's from here. And that's vector, acceleration vector dotted with the normal vector, and that would give us the length of v cross a divided by the length of v. Wowzers. And that would be equal to the square root of the length of a squared minus the length of a sub t squared. Wow, how can all that be true? Well, since a lies in the plane of t and n, the projection of a is equal to the dot product of a and t as a scalar times the unit tangent vector, okay? And normally you would divide that by the length of t, but the length of t is 1, so we don't really have to include that. That's just to remind you. And the projection of a onto vector n is a dot n times, this is a scalar, times the vector n, so the whole thing is a vector, but keep in mind we don't have to divide by the length of n, because the length of n is equal to 1, because it's a unit normal vector. So we have the middle part of the equations above. That's, you know, this part, this part. And since t, the unit tangent vector, is the velocity vector divided by its length, we have the rest of the top, in other words, this part. And since v cross a is the length of v times unit vector t, crossed with the tangential component of acceleration times the unit vector t, unit tangent vector, plus the normal component of the acceleration vector times vector n, the normal vector, that would be the same as if I were to distribute this, right? And notice that t cross t comes out, and the length of v and the tangential component, there's the length of v, there's the tangential component, and then plus distributing this multiplication by this stuff to this, we would get, if I pull this out, you can see length of v times the normal component of acceleration times vector t cross vector n. Okay, note, t cross t is equal to 0. Why is that? Think back to your first test. If the cross product of two vectors is 0 and neither one is a 0 vector, what does that tell you? Remember I said it told you that the two vectors were parallel. Well, vector t is, every vector is parallel to itself, so these are two parallel vectors, so the t cross t is 0. And so that simplifies to just the length of v times the normal component of acceleration times t cross n. Now the length of v cross a is the length of v times the normal component times t cross n, and that would be the length of v as a scalar times a sub n. Remember, this is length, and this is the normal component of acceleration, so that should be okay. And so therefore our an is the length of v cross a over the length of v, and to get the last part, note that the length of a squared is a dot a, so a dot a is equal to all this, which is the same as all this. If I just merely multiplied it out, this times this, this times this, this times this, that means there's two of those, and finally this times this. Keeping in mind that normal vectors cross with themselves is 0, and so, and this dot product would be 0 because the tangential and normal unit tangent unit normal vector are orthogonal, so their dot product is 0. The length of t would be the same as the length of n, which would be 1. So when you have this, there's 1 squared. We have this, well, there's 1 squared. And so what else do we have that simplifies out of all this? The a dot a is just equal to at squared, here it is, times this 1, plus a sub n, this squared. Now, where did this go? Remember that t dot n is equal to 0, so it's at squared plus an squared. So therefore, an, the normal component, and since we have this, if we solved it for an, you'd get this. Don't forget that a dot a is the length of vector a squared. Whew! I hope I'm done. I hope it made sense.
Oh yeah? Oh yeah.
Okay.